Good morning. My name is Emily Smith, and I'm in the 9th grade at Springfield High School. The title of my project is How the Length of a Savonius Wind Turbine Affects the Energy Production. I chose this project because I am very interested in the environmental fields. For the past few years, I have learned about green roofs and solar energy. Throughout last year's project, I wanted to learn about another well-known type of alternative energy, wind power. I researched and found this topic very interesting. I also think that educating the public is important for wind energy to prosper. It can be placed in residential areas and will produce energy at relatively low wind speeds. By having more people know about this type of energy source, more people are likely to use the energy from it and become less dependent on fossil fuels. I also chose this project because I believe alternative energy will help third world countries after a natural disaster, and will ultimately give them better living conditions in the future. Finally, I chose my project because this type of alternative energy is being built on the Lincoln Financial Stadium. This type of energy is powering thousands of homes in the surrounding area. In order to complete my experiment, I researched how air moves to produce wind. Air moves from a higher to a lower pressure. A higher pressure is made when the air molecules are warmer and closer together. The sun forces these molecules closer together due to its heat, and they move around much faster. Sea breeze is also always cooler than land air because of the water cooling properties. The air moves to even out these differences. The wind can be very fast or very slow, depending on the air densities, and can change very quickly. I also researched inertia. Inertia is the tendency of a body to preserve its state of rest or uniform motion unless acted upon by an external force. In other words, it is when an object resists motion because of its mass. It is harder to start to move something that has more mass than something with less mass. Next, I researched different types of wind turbines. There are two categories of wind turbines, vertical and horizontal. The horizontal wind turbines are the most popular ones built and the most well known. They are the ones you might see which have three blades like a propeller on a helicopter. The cost is high initially, but will pay back in about 3 months. The blades are very large to maximize their power output, but will only take up the space at the base, which allows, for example, farming to continue around it. However, because of their large size, they are not a good source of energy for residential areas. Vertical wind turbines are not as well known. They are easier to manage because they are closer to the ground and do not need to have a computer to turn it towards the wind because all sides will be facing the wind. They are smaller, so they can be transported much easier. Finally, they will produce more energy in areas with very fast or very slow wind speeds compared to the traditional horizontal wind turbine. The Savonius wind turbine is relatively unknown. They are in the category of vertical wind turbines. This design can be described as a cylinder cut in half and shifted as shown in this picture. It works by wind pushing on the inside of the cylinder and then circling around to help push it on the other side. The end result is a tube spinning around a central axis, turning a turbine and creating electricity. This first picture shows the most basic type of Savonius wind turbine. It is very stable but produces the least amount of energy. The second picture shows the most complex Savonius wind turbine. It is very efficient because the wind is providing the most force on the first push and then falling through to push it around again. The third picture combines the good aspects of the first two turbines. It is very stable, but allows for the wind to push twice. I will be using this turbine because of these two factors. Because I'm using the third type of Savonius wind turbine, I need to find out the optimal length that should be between the two blades. I did this by using the equation S divided by R, where S is the distance I needed and R was the radius of the half circle. The product should be between 0.1 and 0.15 for best results. I used the distance of 0.765 for my S. After researching, I formed the following hypothesis. If the Savonius wind turbine has a higher height, it will produce a rotation frequency that increases exponentially. I developed this hypothesis by reviewing my research and consulting Mr. Salona, a physics teacher at my school. It was decided that because of the larger amount of surface area on a taller turbine, it would produce more rotations. It would do this because the air would have more area to push the turbine into action. As the length is shortened, there will be less rotations because of the lack of surface area to propel it into motion. However, because it will have less surface area, it will also have less mass. This means that the turbine will have less inertia and will be able to accelerate faster. This will create a graph that resembles an exponential equation. The materials I used to conduct my experiment was a 50-centimeter metal tube with a radius of 7.65 centimeters, a fan with fan settings around 12 kilometers per hour, a .765 centimeter spacer, a timer, ribbon, 10 snips, and 2 fold-back clips. The procedure I used to conduct my experiment was as follows. I established the 30-centimeter height as my control, and I established all other 5-centimeter increments from 15 to 50 centimeters as my variables. I placed the 50-centimeter Savonius wind turbine in the test area 5 centimeters above the ground. I then placed the fan 2 meters away from the turbine, perpendicular to the ground. I allowed the turbine to come to a complete standstill, and then turned the fan on at 12 kilometers per hour. During the 30 seconds, I calculated the number of rotations. I repeated my steps 5 and 6 times, recorded the number of rotations, and found the average. I then used 10 snips to cut off 5 centimeters from the height, and I readjusted the turbine to be in the center of the wind channel. I then repeated steps 7 through 9 until the turbine has a length of 15 centimeters, for a total of 8 tests and 48 trials. I then analyzed my data and drew a conclusion. This graph displays the observed number of rotations for various turbine heights. On my x-axis is the height of the turbine from 10 centimeters to 50 centimeters. On my y-axis is the number of rotations from 15 to 35. On this graph is my data from 50 centimeters to 25 centimeters. For each height, each blue diamond represents one of the 6 trials. However, since my data was very precise, many of my points overlap and only one diamond is shown. The average of the trials for each height is shown as a green triangle. A green line connects the green triangles. As you can tell from this data, the data looks to be exponential, as I stated in my hypothesis. By continuing to cut down my height, I found something very interesting. Instead of my data for the 20 and 15 centimeter turbines to level out and remain around 18 rotations, it jumped up to form a quadratic graph. This could have happened because of the difference in inertia from the taller turbine to the shorter turbine. The inertia must have had a huge impact on the number of rotations. On the taller turbine, the surface area allowed for a lot of wind energy, but the mass caused the turbine to start at a slower rate. On the shorter turbine, there was less surface area, so there was not as much wind energy, but there was less mass. Because the shorter turbines increased their speed, the mass must have had a greater effect on the number of rotations. In conclusion, I learned that my hypothesis was incorrect. When the Savonius' height decreased, the graph looked like a quadratic curve and not an exponential curve. It was also learned that in a Savonius wind turbine, the mass has a greater effect on the number of rotations than the surface area, even though both are important factors. Some improvements that I could make would be to attach the bottom of the turbine to the ground in some way. I would do this because when the turbine got increasingly smaller, it started to sway when the wind first pushed it. This would help me eliminate the swaying. Another improvement that I would make would be to develop another way to secure the 2 half circles together. The foldback clips held the blades together, but they did make the turbine a little shaky. The future experiments following this project could consist of testing this in different speeds of the wind, testing entropy wind patterns to see if the mass has any effect because it would need to start up faster and start down slower, and to test this type of wind turbine to other types of vertical wind turbines. Hi, this is my project from last year. I presented this at my Pennsylvania Junior Academy of Science, or PJAS, regional meet and state meet, and both times I got awarded the high score of first place. I also presented this project at another science fair with the trifold theme. There, I earned the Delco PA Society of Professional Engineers Award, the Delaware County Conservation District Environmental Award, and the first place in the environmental category. Above all, I surprised myself by winning the Best of Fair, which was a huge accomplishment for me. At the Continuation Science Fair, I earned 3rd place in the environmental category and 2nd place in the Society of Women Engineers Award. Thank you for listening. I hope you enjoyed it.